So far, we've been concerned with the response of materials to deformations which lie in the elastic regime. So we gave a certain amount of stress, we wanted to calculate the strain or vice versa, and we based our analysis based on the simple Hooke's law or its generalized form, or anisotropic formulations or thermoelasticity. In all cases, the deformations were reversible. We didn't have to worry about failure, etc. But ultimately, that will be one of our concerns. And one of our concerns, therefore, is going to be the answer to the question, well, how far can I deform this material? How large stresses can I apply to it? And therefore, we're going to talk about a series of topics that may be summarized under the name principal stresses. And eventually, we're going to talk about so-called principal strains as well. And these will help us eventually characterize the extent of the elastic zone within the material behavior. So, the starting point is a simple example. And the starting point is eventually the motivation for what we're about to do. And so, as a simple example, let us do an experiment with two different types of materials. And one material is a metal that can, from our daily life experience again, something that can deform significantly. Not all metals deform significantly, but then again, let's imagine that we have such a material, and the other one is glass. And in both cases, what we're going to do is we're going to simply pull on it. So we have a metal rod or we have a glass rod. And we do this until failure occurs. Now, the characterization and meaning of failure is going to be the content of the next topic. But presently, we have to just associate quickly some meaning to failure. And for a material such as glass, failure could mean the end of the elastic zone at which the rod just breaks apart, because we know that glass doesn't quite display plastic deformation. And when we look at the failure surface of glass, in other words, how this rod breaks, we see that it breaks in this fashion, on a plane that is normal to the axis of loading. Now for metal, again, our failure criteria will be similar. It's going to be, again, the limit to the elastic zone when something happens. But it doesn't break like glass. What's going to happen is it's going to start yielding. And the initiation of yielding ultimately will lead to its failure by, again, breaking, but after significant plastic deformation, which is going to occur from experimental observations as an idealization. We're going to discuss this in more detail, but on a plane that is actually not perpendicular to the axis of loading, but at an angle that is skewed to it. And it turns out that metals fail this way because failure of metals, okay, or let's say initiation of yielding ultimately, is mediated by shear stresses whereas failure of glass is mediated by normal stresses. In other words, the metal is going to start to yield and eventually break on surfaces on which very large shear stresses occur, not necessarily very large normal, but very large shear stresses, whereas glass is going to start to break apart on surfaces on which very large normal stresses occur. And therefore, in general, one of our interests from an analysis point of view is going to be to identify points in a structure, depending on whether it is metallic type material, and those fall in the class of ductile materials. Okay. which are where failure is mediated by shear stresses, okay, depending on whether it's metal or glass, in which case we call the material brittle, breaks easily, if you like. We're going to characterize those in more detail. But depending on what the structure is made of, we are interested in answering the question, well, where does failure occur? And we want to interpret how it occurs. Okay, so in general, we will have some structure. Let's say we have a cylindrical rod or a beam with a cylindrical cross section. And what we are going to do is we are going to apply a combined loading to it, a complicated state of stress will be induced, let's say, throughout the structure. So that would be a torque. And we could also apply a bending moment to it. And then the question is, where does this beam eventually is going to be prone to failure? And how does that failure occur depending on the material properties of this beam? So the content of the topic that we're about to discuss is going to help us in answering questions about failure. And those questions ultimately rest on quantities such as maximum shear stress or maximum normal stress. And therefore, when I am given such a loading, I would like to find out where the maximum shear stress occurs and or where the maximum normal stress occurs throughout the structure. Okay, and now that question is not a trivial question to ask because, well, even at a given point in the structure, say that point, depending on how I make an analysis at that point, there will be different normal stresses and shear stresses that I can observe. Okay, so at a given point, first of all, in a structure that is loaded in a certain way, there will be a certain state of stress. So the state of stress is one and only. Okay, it has a unique interpretation. On the other hand, the way we express it mathematically or quantitatively in terms of numbers, it might change. Now, to clarify that a little bit more, what I'm going to do is I'm going to take a simpler example and just remind you of a simple fact. And we're going to take a simple two-dimensional example, a rod. I'm just going to pull on it. And now I am interested in the state of its stress, say at this point. At that point, I ask you, well, what is the state of stress? And we don't have to really even attach a coordinate system, but you can imagine that, well, at that point, you can say that the state of stress is simply tensile because I'm pulling on it. Okay, well, it is a state of stress that is tensile for sure, or you can interpret it as being such. If you are referring to a plane which is lying perpendicular to the axis of loading. So if I take this free body diagram associated with this blue line, then what I would see is, as one choice, I would see that there is a tensile force here, and I've taken a cross section here that is perpendicular to the axis of loading, and therefore on that surface there is going to be a normal force and hence a normal stress. Let's indicate it like this. That is simply sigma, and there's not going to be any shear stress due to equilibrium of the forces. Good, okay, well, but that was not the only choice I could have made. What I could have done is I could have chosen that surface. So in other words, I could have taken a cut that looks like this. I'm looking at the same point, remember. I'm still looking at the same point. I'm looking at the state of stress at that point. And at that point, now when I take a different surface, well, so first of all, there is a load here, P, but now in order to balance that force, on that surface, sure, the sum of the forces have to be statically equivalent to a force along the horizontal direction. But when I talk about stresses, I talk about normal and shear stresses. So on that plane, there's going to be a normal stress. Let's call that sigma. And eventually, in fact, let's call that sigma prime. And eventually, well, that will cause a net force along that direction. Well, to balance that, there should also be a shear stress. So in this particular case, the shear stress, I can assign it some random direction like this. I know its value has to be negative so that the net vertical components have to balance each other, vertical component of sigma and what I'm going to call tau prime. And so the net force due to tau prime is going to be along that direction, but its value should really be negative, right? I just chose this direction, but because those are our default directions. And so the net force direction-wise is going to be in that direction, tau prime being negative, sigma prime gives a net force along that direction. The statically equivalent representation is again a force that lies along the horizontal direction, which balances the force that I apply. So what is different? Well, what's different is I'm looking at a certain point in a structure. It's a simpler problem where we see things more clearly. At that point, if I take that cross section, there is a normal direction. Associated with that normal direction, there is a normal stress, and there is a shear stress, tau, which in this case is equal to 0. But if I take at the same point a different plane, then the components of the stress, the normal stress on the plane, right? We're on a plane. Along the normal direction, there's a normal stress. Now I call this sigma prime because it's going to be different from sigma. And there's going to be eventually a shear stress to make sure that eventually statically equivalent force resulting from these is along that direction. So all of a sudden, I get a shear stress that is not equal to 0. So therefore, if I were to write the components of the stress as a matrix here, I would have no shear stress, but here I would have a shear stress. So apparently, when I look at a point and I want to talk about the state of stress ultimately has to do with this loading. So it has a unique physical interpretation, but the mathematical representation or the mechanical representation is going to depend on the type of cut I take at that point. And that cut has to do with the coordinate directions. So in this case, really what I'm doing, well, here in this problem, there is a natural coordinate system, if you like. Here there is x and y. And therefore, when I took a cut here, that plane had a normal x and a direction y. So the shear stress is tau x on the plane with normal x in the direction y. So here on the other hand, the coordinate system that's associated with that plane is x prime, let's call it, and y prime. Now, x prime is not equal to x and y prime is not equal to y. So this shear stress is really tau xy prime to indicate that it has to do with this prime coordinate system. So apparently, what is happening is that when the coordinate system or the orientation of the plane alternatively is changing, the components of the stress seem to change. The state of stress, I emphasize again and again that it is one and only. It has a physical meaning here, but the way we interpret it seems to change. Now, in that respect, I would like to talk or emphasize mostly about the mechanical interpretation. And the mechanical interpretation is going to be, in the context of our subsequent discussions, it's going to be that I will take planes at a point that are oriented in different directions. And at those directions, I'll associate with those directions, there will be stress components that will look different. Okay? That is one interpretation. A minor interpretation, strictly equivalent, but mathematically maybe a bit more cumbersome, is to talk about the change of the coordinate system. I'm at a certain point, and with respect to one coordinate system, I like to write the components of the stress. They look like this. With respect to another coordinate system, I am going to write the components of the stress, and they're going to look different. So the stress might have components that change depending on the coordinate system. In that sense, actually, it's very much like a vector. Remember, and I can just make a very quick reminder here. Suppose you had a coordinate system, again, x and y, and you had a vector, and that's the vector. Okay. Now, this is a vector which has a well-defined magnitude and direction, and therefore, with respect to this coordinate system, it will have certain components. It will have an x component, it will have a y component. But the vector, it's a physical quantity like maybe, let's say, velocity, and I understand what it means, what it does. I understand this physical interpretation, but when I want to express its components mathematically, I need a coordinate system. It will have a velocity x, it will have a velocity y, right? But that's not the only coordinate system I can choose. I can choose another coordinate system, and that other coordinate system could have been something like this, right? So this could be an alternative coordinate system, x prime, and the other one, y prime. Still, they are perpendicular to each other, but now the same vector, the same physical component quantity will have a component along only x prime and not along y prime. So all of a sudden, you have a vector represented with respect to the green coordinate system, which has component along only one direction, only one axis, whereas with respect to the original coordinate system, that it has components with respect to both axes. So a vector is physical, but its mathematical representation depends on our coordinate system. So in that sense, stress is something that is similar. State of stress is physical, and we should emphasize that, okay? And that doesn't change, but the way we represent it might change depending on the cuts we take. At a point, we're always at a point, or alternatively, I can say that the coordinate system changes, okay? But the coordinate system is induced, notice, it's not arbitrary, it's induced by the cut that we are taking. So it's induced by the surface that we are choosing. But again, going back, we are always at the same point. We're just taking different cuts, and the stress view changes. Now, for that reason, if for a given load, failure is going to occur here, we should be able to predict failure either with that or that picture. However, if failure is going to occur on a plane where a very large normal or a very large shear stress is going to occur, then among all the possible cuts that I can take, a vertical cut like this or a cut like that, or for that matter, some other cut of arbitrary orientation, among those, let's say for a metal, failure is going to occur on a plane where the shear stress is not zero, but it reaches some very large value, the maximum value, let's say, possible. That's where it's going to occur. So I need to search at a point among all planes. I need to find the cut, the plane, the orientation on which the shear stress is largest, because that's where failure is going to be initiated. So that's sort of the underlying motivation behind everything that we are trying to do. So finally, let me also complicate this picture a little bit further and draw the following. So first of all, I'm always looking at a point. This is the force, this is the stress distribution. What I could have done is I could have sort of zoomed onto a certain point in the vicinity of that single point, and in the vicinity of that point, I could have stated the state of stress, okay, geometrically. And our geometric representation is a normal stress along that direction and nothing else in the other direction according to my description. Now, in this alternative picture, what I'm really doing is, at that same point, instead of taking a element that's oriented like this, at the same point, I'm picking an element that is oriented in a slightly different way, at a certain orientation. So that is now the new orientation, again, at the same point in the structure. So the geometric representation is also associated with some different orientation of my element. And now there is a normal stress sigma prime, and there is a shear stress as well, which is tau prime. Okay. Now, I am not drawing the normal stress on this plane. Okay. There will be, in general, normal stress on that plane. Let me just draw it, but not write its magnitude. We will eventually find all of those things strictly. And so that's just sigma prime. But I know that the shear stress on that plane is the same due to the symmetry of the stress. And it's going to be tau prime once again. Okay, so this value of the shear stress, of the normal stress, let's put an exclamation mark there, because it turns out the picture is going to be one where there will be in general normal stresses on those planes as well. Okay, all right, good. So that is the motivation that we have. We want to look at a point, we want to search different planes such that I can characterize eventually material failure or the onset of material failure, let's say, put more correctly, in a rigorous manner. Okay, so our therefore focus is going to be for a given state of stress at a given point in the structure. If I know the state of stress or the loading, let's say, with respect to one coordinate system, well, how do the components of the stress change for that given same state of stress? How do they change when I take a different cut or when I change my coordinate system? Okay, when the orientation of the surface changes. Okay, or in other words, when this picture changes. This is the picture with respect to the XY coordinate system. That's the picture with respect to this rotated coordinate system. And I'd like to find the components of the stress with respect to this coordinate system. So here the stress eventually forms a matrix that looks like this, omitting the third direction. So strictly 2D, if you like, it is sigma 0, 0, 0. There is no normal stress associated with the perpendicular direction. Here the stress looks like this. It is a sigma prime associated with that direction, tau prime, tau prime. Here, I don't know yet. That's my exclamation mark. Okay, but that's the way the stress looks here, and that's the way the stress looks here. Okay, let's put a prime to indicate that that's associated with a new state of stress. All right, good. So that is what we would like to ultimately answer. How do the components of the stress change when I change my orientation of the planes? So now we would like to characterize that mathematically and go ahead and obtain explicit expressions for the components of the stress when at a point the orientation of the coordinate system or the normal of the plane, if you like, which characterizes that cut, changes.